Welcome to Deep Science Sleep. Take a deep breath. Find yourself a comfortable position, one where you can settle in completely, allowing your body to sink into whatever surface supports you. Perhaps you're lying in bed, or maybe you're nestled into your favorite chair. Wherever you are, let yourself arrive fully in this moment. Close your eyes if you'd like, or let them rest softly on a nearby point. We're about to embark on a gentle journey through the cosmos, exploring the most calming, most soothing truths about the stars that fill our night sky. There's no rush, no urgency. Time moves differently here, in this quiet space we're creating together. The universe is vast and patient, and tonight, will match its rhythm. Let the tensions of your day begin to dissolve like morning mist under gentle sunlight. We're going to discover together how the stars above us offer not just beauty, but a profound sense of peace, a reminder of our place in something infinitely larger and wonderfully serene. The ancient light reaching us. When you look up at the night sky on a clear evening, something remarkable happens that most people never pause to consider. The light entering your eyes at that very moment began its journey years ago, sometimes centuries ago, occasionally millions or even billions of years ago. This simple fact transforms every glance skyward into a form of time travel, a window into the past that requires no machine, no special training, only the patience to look up and see. Consider our sun, that brilliant sphere that warms our days and makes life on Earth possible. When you see sunlight streaming through your window in the morning, that light actually left the sun's surface 8 minutes and 20 seconds earlier. The photons dancing on your skin, illuminating the room around you, began their journey nearly 9 minutes before they reached you. The sun sits approximately 93 million miles away from Earth, and even traveling at the cosmic speed limit of about 186,000 miles per second, light still needs those precious minutes to complete its voyage. But the sun is our cosmic neighbor, practically next door in astronomical terms. The nearest star system beyond our sun is Alpha Centauri, a triple star system that includes Proxima Centauri, the closest individual star to Earth. Proxima Centauri resides at a distance of roughly 4.24 light-years from us. This means that when you spot this dim red dwarf through a telescope, the light you're seeing departed from that star over 4 years ago. If Proxima Centauri were to vanish this instant, completely winking out of existence, we would continue to see it shining in the sky for another 4 years before its absence became apparent. The light already in transit would still arrive, still enter our telescopes, still tell us stories of a star that no longer exists. This disconnect between the present moment and what we observe creates a gentle, meditative quality to stargazing. When you look at Sirius, the brightest star in our night sky, you see it as it was 8.6 years ago. The blue-white light that catches your eye tonight left Sirius when the world was slightly different, when you were slightly different. Perhaps you were in school or starting a new job, or meeting someone who would become important in your life. The photons traveling toward you were oblivious to all of this, simply making their straight-line journey through the void. Venture further into the cosmos, and the temporal distances become even more profound. Betelgeuse, that reddish star marking the shoulder of Orion, shines at us from approximately 550 light-years away. When you admire this massive red supergiant on a winter evening, you're seeing light that departed during the Renaissance, when Leonardo da Vinci was painting the Mona Lisa, when the printing press was revolutionizing human knowledge. The Betelgeuse we observe tonight might have already exploded in a spectacular supernova, but we won't know for centuries because the light carrying that information hasn't reached us yet. Deneb, another brilliant star that forms part of the Summer Triangle, lies even further away at roughly 1,400 light-years. The light from Deneb that sparkles above you tonight began its journey around the year 620 in the Common Era. When those photons left Deneb's surface, Muhammad had recently begun preaching in Mecca, the Tang dynasty was flourishing in China, and the Maya civilization was at its height in Central America. Those photons have been traveling through space for the entire span of human history from that point forward, witnessing nothing, interacting with almost nothing, simply moving forward at their constant, unwavering speed. The Pleiades star cluster, that beautiful collection of young blue stars that resembles a tiny dipper to the unaided eye, sits about 440 light-years distant. When you gaze at these sisters of light, you see them as they appeared in the late 1500s, during the Elizabethan era in England, when Shakespeare was writing his plays. The light carrying the image of these stars to your eyes is a message from the past, a time capsule of ancient photons that have journeyed across the galaxy to reach you. There's something deeply calming about this reality. It reminds us that the universe operates on timescales far beyond our daily worries and concerns. The stress of an upcoming deadline, the anxiety about tomorrow's obligations, the regrets about yesterday's mistakes, all of these shrink into insignificance when you realize you're looking at light that has been traveling since before your great-great-grandparents were born. The stars teach patience. They teach perspective. They show us that time is vast and strange and wonderful, and that our small moment within it is but one heartbeat in a cosmic symphony that has been playing for eons and will continue long after we're gone. Even more astonishing, when we train our most powerful telescopes on the deepest reaches of space, we can see galaxies so distant that their light has been traveling for over 13 billion years. The Hubble Extreme Deep Field, a photograph taken by the Hubble Space Telescope, captures galaxies as they appeared when the universe was only 600 million years old, just a tiny fraction of its current age of 13.8 billion years. These galaxies shine from a time when the first stars were forming, when the structure of the cosmos was just beginning to take shape. The light in that image is older than our entire solar system, older than Earth itself, older than anything on our planet. This phenomenon, this looking back in time, happens because light moves at a finite speed. While 186,000 miles per second seems incomprehensibly fast by human standards, on cosmic scales it becomes almost leisurely. The universe is so immense that light itself must journey for years, centuries, or eons to cross from one point to another. And this creates a beautiful consequence. The sky above us is not a snapshot of the present, but rather an archive of history, a museum of cosmic events occurring at different points in time, all visible simultaneously. Think about what this means. When you look at two stars side by side in the sky, you might be seeing one as it was 50 years ago and another as it was 500 years ago. They appear to be contemporaries, neighbors in space, but you're actually observing them at completely different moments in their existences. The night sky is a collage of different eras, different epochs, all presented together in one glorious display. There's a profound peace in accepting this. We cannot change the past. What happened to those stars decades, centuries, or millennia ago is fixed, immutable. The light carrying that information is already on its way to us, and nothing can alter it. In the same way, The light leaving Earth right now will tell future observers about our planet as it exists in this moment, regardless of what happens next. The present becomes the past, becomes a message to the future, all encoded in photons racing through the void. And yet, despite this journey through time, when that starlight finally reaches us, it arrives fresh and vivid, ready to paint images on our retinas and fire neurons in our brains. The photon that enters your eye tonight from a distant star is the same photon that left that star centuries ago. It hasn't aged. It hasn't changed. It simply is existing in a strange temporal state where, from the photon's perspective, no time passes at all. According to Einstein's relativity, a photon experiences no time during its journey. For the photon, the moment it leaves the star and the moment it enters your eye are the same instant, even though centuries pass for the rest of the universe. This creates a beautiful paradox. We are watching ancient history, yet we're also connecting with those distant stars in a timeless present. The act of observation collapses past and present together. The star as it was and the light as it is merge into a single experience, a single moment of perception where time becomes fluid and mysterious. As you drift towards sleep tonight, imagine those photons arriving at Earth from all across the galaxy, from all across the universe. Each one a messenger from the past, each one carrying information about a distant time and place. They arrive constantly, ceaselessly, whether we observe them or not. Right now, as you rest, photons from stars that died 1,000 years ago are landing on Earth, their final act to tell us about worlds that no longer exist. And tomorrow night, and the night after, new photons will arrive, and the ancient light show will continue, patient and eternal, waiting for anyone who cares to look up and witness the beautiful melancholic fact that we are all time travelers, whether we realize it or not. The life cycles of stars. Stars are not eternal, unchanging points of light, though they might seem that way during our brief human lifespans. Each star follows a life cycle as predictable and natural as the seasons, though played out across timescales so vast they make our longest human civilizations seem like brief flickers. There is something deeply comforting about the reliability of stellar evolution, the way each star moves through its stages according to laws as certain as gravity itself. A star is born when a vast cloud of gas and dust, a molecular cloud floating in the space between existing stars, begins to collapse under its own gravity. These clouds are called stellar nurseries, and they're among the most beautiful and serene regions in the galaxy. Imagine a cloud of gas so enormous it might span dozens of light years across, containing enough material to form hundreds or thousands of stars. The cloud is cold, typically only 10 to 30 degrees above absolute zero, that theoretical point where all molecular motion ceases. In this frigid, dark environment, hydrogen molecules cluster together, slowly, gently, pulled by the patient tug of gravity. Perhaps a nearby supernova sends a shock wave through the cloud, compressing part of it. Or maybe random density fluctuations cause one region to have slightly more mass than its surroundings. Whatever the trigger, once a pocket of gas becomes dense enough, gravity takes over as the dominant force. The gas begins to fall inward, accelerating as it goes, pulling more material with it. This is not a violent process, despite what words like collapse might suggest. It unfolds over hundreds of thousands or millions of years, a gradual gathering of matter, a slow crescendo of density and temperature. As the cloud contracts, the particles within it collide more frequently. Each collision converts a tiny amount of gravitational potential energy into heat. The center of the collapsing cloud grows warmer. After thousands of years, a dense core forms at the center, surrounded by a swirling disk of gas and dust. This core is a protostar, not yet a true star, but well on its way to becoming one. It glows dimly in infrared wavelengths, too cool to emit visible light but warm enough to radiate heat. The protostar continues to accrete mass from the disk around it, growing larger and denser and hotter with each passing millennium. Eventually, after perhaps 10 million years of gradual contraction, the core temperature reaches a critical threshold, about 10 million degrees Kelvin. At this temperature, hydrogen atoms, stripped of their electrons by the intense heat, collide with such force that they overcome their mutual electromagnetic repulsion and fuse together. Four hydrogen nuclei combine to form one helium nucleus in a process that releases tremendous energy. This is nuclear fusion, the reaction that powers stars, and once it ignites, everything changes. The protostar becomes a star. The energy released by fusion creates an outward pressure that halts the gravitational collapse. The star reaches a state of hydrostatic equilibrium, a perfect balance between the inward pull of gravity and the outward push of radiation pressure. This balance is extraordinarily stable. A star can maintain it for billions of years, peacefully fusing hydrogen in its core, radiating energy into space, existing in a state of cosmic contentment. Our Sun is in this phase now, called the main sequence, and has been for about 4.6 billion years. It will continue in this stable state for another 5 billion years or so. During this entire span, nothing dramatic happens. The Sun simply shines, converting hydrogen to helium, maintaining its size and temperature, providing steady, reliable energy to Earth and the other planets. This is the longest phase of a star's life, a period of stability and predictability that can last, for stars like our Sun, for 10 billion years total. But nothing lasts forever. Eventually, the hydrogen fuel in the star's core runs out. For a star like the Sun, this happens after about 10 billion years. When the core hydrogen is exhausted, fusion stops, and without the outward pressure from fusion reactions, the core begins to contract again under gravity. This contraction heats the core, and soon the temperature rises enough that hydrogen fusion begins in a shell around the core. This shell fusion produces even more energy than the core fusion did, causing the outer layers of the star to expand dramatically. The star becomes a red giant, growing to perhaps 100 times its original diameter. Its surface cools to around 3,000 or 4,000 degrees Kelvin, giving it a reddish appearance, but the star's overall luminosity increases because its surface area has become so enormous. For low to medium mass stars like our Sun, the core eventually becomes hot enough, around 100 million degrees Kelvin, for helium fusion to begin. Helium nuclei fuse to form carbon and oxygen. This helium burning phase lasts only a few hundred million years, a tiny fraction of the star's main sequence lifetime. The star might pulse and vary in brightness as fusion proceeds in complex shells around the core, burning different elements at different radii. Eventually, for stars of solar mass or slightly larger, the core becomes degenerate, a state where matter is packed so tightly that quantum mechanical effects prevent further compression, even as fusion ceases. The star's outer layers drift away in gentle waves, forming a planetary nebula. a beautiful shell of glowing gas expanding into space at perhaps 20 or 30 kilometers per second. Left behind is the star's core, a white dwarf, a dense ember about the size of Earth but containing roughly half the sun's mass. This white dwarf no longer generates energy through fusion. It simply radiates away its stored thermal energy, slowly cooling over billions of years, gradually fading from white to yellow to red to brown to black. A white dwarf can take longer than the current age of the universe to cool completely, so none have yet faded to true black dwarfs. They simply persist, patient and unchanging, monuments to stars that once were. For more massive stars, those with more than about 8 times the sun's mass, the end is more dramatic but no less predictable. These stars burn through their hydrogen much faster because their greater mass creates higher core temperatures and pressures. A star of 20 solar masses might spend only 10 million years on the main sequence, compared to the sun's 10 billion. After exhausting their core hydrogen, massive stars don't stop at helium fusion. Their cores are hot enough and dense enough to continue fusing heavier elements. Carbon fuses to form neon and magnesium. Neon fuses to form oxygen and magnesium. Oxygen fuses to form silicon and sulfur. Silicon fuses to form elements around iron. This process creates layers within the star, like an onion, each shell fusing different elements. The outermost layers still fuse hydrogen. Below that, helium fusion occurs. Deeper still, carbon burns, then neon, then oxygen, then silicon, each layer progressively smaller and hotter and denser. At the very center sits a core of iron and nickel. Iron is significant because it represents a boundary. Fusion of elements lighter than iron releases energy. Fusion of elements heavier than iron requires energy. Once a star's core has been converted to iron, no more fusion energy can be extracted. The core has reached the end of the nuclear road. What happens next occurs incredibly quickly by stellar standards. The iron core, no longer supported by fusion energy, collapses under its own gravity in less than a second. The core compresses to nuclear densities, at which point the collapse halts abruptly as the neutrons packed in the core resist further compression. The infalling outer layers of the star crash into this suddenly rigid core and rebound. A shock wave races outward through the star at tremendous speed, heating the stellar material to billions of degrees and blowing the star apart in a core collapse supernova, one of the most energetic events in the universe. During this explosion, which lasts only a few seconds, the intense conditions allow for the creation of elements heavier than iron. Gold, platinum, uranium, all the heavy elements on the periodic table. These newly forged atoms are blasted into space at thousands of kilometers per second. The explosion can outshine an entire galaxy for weeks or months before fading. Left behind is either a neutron star, an object about 20 kilometers across with the mass of our sun, or, if the original star was massive enough, a black hole. There's something profoundly peaceful about this cycle, despite the violence of supernovae. Stars are born, live stable lives for vast stretches of time, and then, at the end, return their material to the interstellar medium. The heavy elements created in stars and supernovae mix with the interstellar gas, enriching it, making it possible for future generations of stars to form with planets and, potentially, life. Every atom of carbon in your body was forged in the core of a dying star. Every atom of iron in your blood was created in a supernova explosion. The calcium in your bones, the oxygen in your lungs, the nitrogen in your DNA, all of these elements are the products of stellar alchemy, donated to the universe by stars that lived and died long before our solar system existed. We are, quite literally, made of stardust. This isn't poetic exaggeration. It's sober scientific fact. The atoms comprising your body have been recycled through multiple generations of stars, each one adding new elements, new complexity, new possibilities. You are a collection of ancient stellar materials, temporarily organized into a thinking, feeling form, composed of matter billions of years old that has journeyed across the galaxy to become part of you. This continuity, this recycling of matter from star to space to cloud to star again, creates a sense of connection to the cosmos that goes beyond mere metaphor. Stars die so that we might live. The sun will eventually shed its outer layers, returning most of its mass to the galaxy. Some of that material might, in the distant future, become part of a new star, a new planetary system, perhaps even new life. Nothing is wasted. Nothing is lost. Matter transforms, energy flows, but the substance of the universe persists, cycling through forms, creating beauty and complexity at every turn. As you rest tonight, picture this grand cycle playing out across the galaxy. In the Orion Nebula, 1,500 light-years away, new stars are being born this very moment from clouds of gas enriched by ancient supernovae. In other regions, red giants are pulsing gently, nearing the end of their lives, preparing to return their gifts to the cosmos. Somewhere, though we might not see it for years, a massive star is exploding, seeding its surroundings with heavy elements that will, millions of years from now, become part of planets and perhaps living beings. The cycle continues, has continued for billions of years, and will continue for billions more. Stars are the great recyclers of the cosmos, patient and generous, transforming simple hydrogen into the complex chemistry of life, then offering those products back to the universe to begin again. The chemistry of stardust. The idea that we are made of stardust has captured human imagination for generations, but the full story of stellar nucleosynthesis, the creation of elements inside stars, is even more remarkable than most people realize. It's a story of transformation and creation, of how the universe bootstrapped itself from the simplest element to the full complexity of the periodic table, all through the patient work of stars over billions of years. In the beginning, shortly after the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. These elements formed during the first few minutes of cosmic history, when the entire universe was hot enough and dense enough for fusion to occur everywhere at once. As the universe expanded and cooled, this brief epoch of primordial nucleosynthesis ended, leaving the cosmos with a composition that was roughly 75% hydrogen and 25% helium by mass, with everything else making up less than 1%. This was the raw material from which the first stars would form, simple and limited, containing none of the heavier elements that make planets and life possible. The first generation of stars, called Population 3 stars, were massive objects composed almost entirely of hydrogen and helium. They were short-lived, burning brilliantly for only a few million years before exploding as supernovae. But in their brief lifetimes, they created something new. In their cores, hydrogen fused into helium, and in the most massive ones, helium fused into carbon, oxygen, neon, magnesium, and heavier elements. When these stars exploded, they dispersed these newly created elements into the surrounding space, enriching the interstellar medium for the first time with what astronomers call metals, any element heavier than helium. The next generation of stars, population 2 stars, formed from clouds already containing a small fraction of these heavy elements. These stars could be smaller and longer-lived than their predecessors, and they continued the work of element creation. In their cores, fusion reactions built heavier and heavier nuclei through a series of well-understood processes. The proton-proton chain, the dominant fusion process in stars like our Sun, converts 4 hydrogen nuclei into 1 helium nucleus. This happens in several steps involving intermediate particles and neutrinos, but the net result is that mass is converted to energy according to Einstein's famous equation, E=mc², and hydrogen becomes helium. Once a star exhausts its core hydrogen, it can, if massive enough, begin fusing helium. 3 helium nuclei combine through the triple alpha process to form carbon. This process is exquisitely sensitive to the exact physical constants of the universe. Change them slightly and carbon wouldn't form, and without carbon, life as we know it couldn't exist. For helium nuclei fuse to create oxygen. 5 helium nuclei create neon. This process of alpha capture, where helium nuclei attach to existing heavier nuclei, builds up the elements in steps. Stars more massive than about 8 solar masses can ignite successive fusion stages, each one burning a different fuel and creating still heavier elements. Carbon fusion produces neon, magnesium, and sodium. Neon fusion, which actually involves photodisintegration followed by recombination, produces oxygen and magnesium. Oxygen fusion creates silicon, sulfur, phosphorus, and other elements around mass 16. Finally, silicon fusion produces the iron peak elements: iron, nickel, cobalt, chromium, and their neighbors in the periodic table. This onion shell structure of fusion stages in a massive star's final days is a beautiful example of ordered complexity emerging from simple processes. Each shell operates independently, fusing its particular fuel at its particular temperature and density, all maintained in equilibrium by the balance of gravity and pressure. The star has become a cosmic factory, simultaneously running multiple assembly lines, each producing different products at different rates. But fusion stops at iron, as we mentioned earlier, because iron is at the peak of the binding energy curve. Fusion of iron nuclei into heavier elements doesn't release energy. It requires energy. So once a massive star's core becomes iron, fusion energy generation ceases. The end comes quickly after that, leading to a core collapse supernova. But it's during the supernova itself that elements heavier than iron are created. During the explosion, conditions become so extreme that nuclear processes not possible during a star's normal life become energetically favorable. 2 main processes create heavy elements: the R process, or rapid neutron capture process, and the S process, or slow neutron capture process. The S process occurs in the late stages of a massive star's life and in certain types of old stars. Neutrons are captured by atomic nuclei slowly enough that unstable nuclei have time to beta decay, converting neutrons to protons before capturing additional neutrons. This creates a diagonal path up the periodic table, producing about half of the elements heavier than iron. The R process occurs during supernovae and, as recently discovered, during neutron-star mergers. A flood of neutrons, produced by nuclear reactions in the extreme environment, bombards atomic nuclei faster than they can decay. Nuclei capture many neutrons in rapid succession, building up neutron-rich isotopes, which then undergo multiple beta decays after the neutron flux subsides, creating stable, heavy elements. The R process is responsible for the other half of the heavy elements, including gold, platinum, uranium, and thorium. Every gold atom in existence was created in one of these cataclysmic events, either a supernova or a collision between neutron stars. The gold in your jewelry, if you wear any, is the debris from stellar explosions that occurred billions of years ago, before our solar system even existed. When you consider that it takes such extreme conditions to create gold, that it requires the death of stars or the merger of their remnants, gold's rarity becomes understandable. It's not just rare on Earth. It's rare in the universe because the processes that create it are so uncommon and so violent. The same is true for many other elements. Iodine, essential for human thyroid function, is produced only in the R process. Lead, often thought of as commonplace, is actually the end product of long radioactive decay chains that begin with uranium and thorium, themselves products of neutron capture. Even lighter elements that aren't made in significant quantities by fusion, like lithium, beryllium, and boron, are created by cosmic ray spallation, a process where high-energy particles smash into heavier atoms and break them into lighter fragments. When our solar system formed 4.6 billion years ago, the molecular cloud from which it condensed had already been enriched by countless generations of stars. The heavy elements in that cloud had been cooked up in stellar cores and supernova explosions and then mixed back into the interstellar medium. Our Sun is a third-generation star, possibly even later, containing in its outer layers small but crucial amounts of these heavy elements. Earth, and by extension you, formed from the small fraction of the solar nebula's mass that was not hydrogen or helium. The rocky planets, the asteroids, the moons, all of these are made almost entirely from heavy elements created in stars. Your body, specifically, is a catalog of stellar processes. The hydrogen in your water molecules is primordial, left over from the Big Bang. The carbon that forms the backbone of every organic molecule in your cells was created by helium fusion in red giant stars. The nitrogen in your amino acids and DNA came from the CNO cycle in massive stars. The oxygen you breathe, the oxygen in your water and in virtually every biological molecule, was made by helium fusion and, in greater quantities, by oxygen fusion in massive stars. The iron in your hemoglobin, allowing your blood to carry oxygen, was forged in silicon fusion and supernova explosions. The calcium in your bones came from oxygen fusion and supernovae. The phosphorus in your DNA and ATP was created in supernovae. Trace elements tell the same story. The zinc in your enzymes, the copper in your proteins, the selenium in your antioxidant systems, the molybdenum in your bacterial cofactors, all of these were created in dying stars and supernovae. The iodine in your thyroid came from R-process nucleosynthesis. Even elements in your body that serve no biological function but are present anyway, like lead from environmental exposure, carry this same cosmic heritage. There's something profoundly moving about this realization. You are not separate from the cosmos. You are the cosmos experiencing itself, a local arrangement of stellar matter that has, through the patient working of chemistry and evolution, become capable of contemplating its own origins. The atoms in your hand right now have been on an incredible journey. They were created in stellar furnaces or explosive cataclysms. They drifted through space for millions or billions of years as part of the interstellar medium. They were swept up into the molecular cloud that would become our solar system. They were part of the protoplanetary disk, perhaps spending time in asteroids or comets. Eventually, they found their way to Earth, where they cycled through rocks and water and atmosphere, possibly passing through countless organisms before becoming part of you. They have been recycled and reused, never destroyed, simply rearranged, for billions of years. And when you die, those atoms will continue their journey. Your carbon will return to the atmosphere as carbon dioxide, perhaps to be taken up by a plant in photosynthesis, becoming part of a tree or a blade of grass. Your nitrogen will feed bacteria in the soil. Your calcium and phosphorus will cycle through ecosystems. In a sense, you are borrowing these atoms briefly, holding them in your particular configuration for the few decades of your life, and then returning them to Earth's active cycle. Nothing is lost. Matter persists. The atoms don't care what form they take. They simply continue existing as they have since their creation in a star. This continuity across time and space, this recycling of matter from stars to planets to life and back again, is one of the universe's most elegant patterns. It means we are all connected, not just to other humans, but to the planet, to the solar system, to the galaxy, to the grand cycles of stellar birth and death. When Carl Sagan said we are made of star stuff, he was describing a literal truth, a genealogy that traces back billions of years to stars whose names we will never know but whose legacy comprises our physical existence. As you settle into rest tonight, feel the weight of your body, composed of these ancient atoms. Each one has its own history, its own journey from a stellar core to your flesh and bone. They've survived unimaginable conditions, traveled unimaginable distances, and now, for this brief moment, they are you. There is no separation between you and the stars. You are the universe made manifest, stardust made conscious, the product of billions of years of cosmic evolution, intimately linked to everything that has ever existed in the heavens above. The sounds and colors of stars. Although space is a vacuum and sound cannot travel through it, stars are far from silent. They vibrate and oscillate in complex patterns, and if we could hear them, each would have its own unique voice, its own song. The science of astroseismology, which studies these stellar oscillations, has revealed that stars ring like bells, pulsing rhythmically as pressure waves travel through their interiors. These vibrations create changes in the star's brightness and spectral characteristics that we can detect and measure from Earth, allowing us to hear the stars through careful observation, even if sound waves never reach us. Our sun, for instance, vibrates with millions of different oscillation modes simultaneously. These are essentially sound waves trapped inside the sun, traveling through the solar interior, reflecting off the sun's surface and core, interfering with each other to create complex patterns of expansion and contraction. The most prominent oscillations have periods of about 5 minutes, meaning the sun's surface rises and falls rhythmically every 5 minutes, though the displacement is only a few hundred meters, tiny compared to the sun's 1.4 million kilometer diameter. By studying these oscillations, astronomers have been able to map the sun's internal structure with remarkable precision, determining the temperature, density, and composition at different depths, all without ever directly observing the interior. Different types of stars have different characteristic pulsations. Red giant stars often pulsate with periods of days or months, swelling and shrinking in a regular rhythm as pressure waves travel through their expanded envelopes. Some stars, like Cepheid variables, pulsate so dramatically that their brightness changes by several magnitudes over periods of days to weeks, making them visible across intergalactic distances and invaluable as distance indicators. Other stars, like RR Lyrae variables, pulsate more rapidly with periods under a day. These rhythms are not arbitrary but are determined by the star's mass, size, and internal structure, making them cosmic clocks that tick at rates set by fundamental physics. The color of a star tells us about its temperature, and temperature reveals much about a star's life stage and mass. Stars are classified by their spectral types, traditionally remembering using the mnemonic, "Oh, be a fine girl, kiss me," representing the sequence O, B, A, F, G, K, M, from hottest to coolest. This sequence isn't arbitrary. It's a temperature scale discovered through careful analysis of stellar spectra in the early 20th century. O-type stars are the hottest visible stars, with surface temperatures exceeding 30,000 Kelvin. They appear blue-white to the human eye and emit most of their energy in the ultraviolet portion of the spectrum. These are massive stars, typically more than 16 times the Sun's mass, and they burn through their fuel so quickly that they only live for a few million years. The hottest O-type stars can reach temperatures above 50,000 Kelvin, making them furnaces beyond human comprehension. Their spectra show lines from ionized helium, indicating temperatures so extreme that even helium atoms have been stripped of electrons. B-type stars, like Rigel in Orion, have surface temperatures between 10,000 and 30,000 Kelvin. They still appear bluish-white but less intensely blue than O-type stars. These stars are also massive and short-lived, though not quite to the extreme of O-type stars. They show neutral helium lines in their spectra and are perhaps 4 to 16 times the Sun's mass. A-type stars, the classic example being Vega and Sirius, have temperatures between 7,500 and 10,000 Kelvin. They appear white to the human eye with perhaps a slight blue tint. Their spectra show the strongest hydrogen absorption lines of any stellar class because at their temperatures, hydrogen is most often in the right energy state to absorb light at visible wavelengths. A-type stars are typically about 1.4 to 2.1 times the Sun's mass and have lifetimes of about 1 to 2 billion years. F-type stars, like Procyon, have surface temperatures between 6,000 and 7,500 Kelvin and appear yellow-white. They're intermediate between A-type and G-type stars in most properties and have masses between 1.04 and 1.4 solar masses. They can live for 3 to 6 billion years on the main sequence. G-type stars, including our own Sun, have temperatures between 5,200 and 6,000 Kelvin. They appear yellow to the human eye, though the Sun looks white from space because our atmosphere scatters blue light more effectively than red, making the Sun appear yellower from the surface. G-type stars have masses between 0.8 and 1.04 solar masses and can live for 10 billion years or more. Their spectra show strong lines from ionized calcium and neutral metals like iron. K-type stars, such as Alpha Centauri b and Epsilon Eridani, have temperatures between 3,700 and 5,200 Kelvin. They appear orange to the human eye and are smaller and cooler than the Sun, typically between 0.45 and 0.8 solar masses. Because they burn their fuel more slowly, K-type stars can live for 15 to 30 billion years, longer than the current age of the universe. Their spectra show strong lines from neutral metals. M-type stars are the coolest visible stars, with temperatures below 3,700 Kelvin. They appear red or reddish-orange and are the most common stars in the galaxy, making up about 76% of all stars. Despite their abundance, they're so dim that none are visible to the naked eye except for a few that are particularly close to us. M-type stars range from about 0.08 solar masses, the minimum mass needed for hydrogen fusion, up to about 0.45 solar masses. The smallest ones can live for trillions of years, slowly sipping their hydrogen fuel. Their spectra show molecules like titanium oxide that can only exist in the relatively cool temperatures of their atmospheres. Recently, astronomers added 3 more spectral classes for objects even cooler than M-type stars: L, T, and Y. These are brown dwarfs, objects too small to sustain hydrogen fusion but still glowing from their formation heat and, in some cases, from fusion of deuterium. L dwarfs have temperatures between 1,300 and 2,000 Kelvin and show metal hydrides and alkali metals in their spectra. T dwarfs, between 600 and 1,300 Kelvin, show methane absorption. Y dwarfs, the coolest known, can be as cold as room temperature, around 300 Kelvin, and emit most of their light in the infrared. These objects blur the line between stars and planets, existing in a twilight zone of cosmic classification. The relationship between color and temperature is a direct consequence of blackbody radiation, a fundamental principle of physics. All objects emit electromagnetic radiation based on their temperature, and the spectrum of that radiation follows a predictable curve. The peak wavelength of emission moves to shorter, bluer wavelengths as temperature increases. Wien's displacement law quantifies this relationship. The peak wavelength in nanometers equals 2,898,000 divided by the temperature in Kelvin. For a star at 5,778 Kelvin like the Sun, the peak wavelength is about 502 nanometers, right in the middle of the visible spectrum in the green-yellow range. But stars emit radiation across all wavelengths, not just at the peak, which is why the Sun appears white, emitting significant energy in all visible colors, rather than appearing green. Hot blue stars emit most of their energy at short ultraviolet wavelengths, but they still emit plenty of visible light, weighted toward the blue end of the spectrum. Cool red stars emit most of their energy in the infrared, but enough visible light leaks into the red part of the spectrum to give them their characteristic color. The human eye evolved to be most sensitive to the wavelengths where the Sun emits most of its visible light, which is not coincidental. Our Sun's characteristics shaped the evolution of vision on Earth. Stellar spectroscopy, the analysis of starlight broken into its component wavelengths, reveals far more than just temperature. Each element in a star's atmosphere absorbs light at specific wavelengths, creating dark absorption lines in the star's spectrum. These lines are as unique as fingerprints, allowing astronomers to determine precisely which elements are present in a star and in what quantities. Hydrogen, helium, iron, calcium, sodium, magnesium, and dozens of other elements each leave their signature in stellar spectra. By comparing the strength of different absorption lines, astronomers can determine not just temperature but also surface gravity, atmospheric pressure, chemical composition, and even the star's motion toward or away from us. If a star is moving toward Earth, its spectral lines shift slightly toward shorter, bluer wavelengths, a phenomenon called blue shift. If moving away, the lines shift toward longer, redder wavelengths, creating a redshift. This Doppler effect allows precise measurement of stellar velocities, revealing that stars orbit the galaxy's center, that binary stars orbit each other, and that some stars vary their radial velocity as planets tug on them, betraying the presence of unseen companions. The colors we observe in stars have been traveling to us for years or centuries, carrying information about conditions in stellar atmospheres from the past. When you look at red Betelgeuse, you're seeing red photons that escaped from its cool, extended atmosphere 550 years ago. When you admire blue Rigel, you're observing light from a stellar surface so hot it would vaporize any material we know in an instant, light that began its journey 860 years ago. Each star's color is a message about its nature, encrypted in the wavelength distribution of its light. There's something meditative about understanding this connection between color and cosmic reality. The beautiful variety of colors we see in the night sky, the reds and blues and yellows and whites, aren't mere decoration but are instead information, data encoded in photons, telling us about temperatures and compositions and stages of stellar evolution. The universe communicates with us through light, and once you learn the language, every star you see becomes more than just a point of light. It becomes a story, a set of physical facts, a place with real characteristics, as real as the ground beneath your feet. And though stars themselves produce no sound in the vacuum of space, those internal oscillations create pressure changes that, if you could somehow experience them directly inside a star, would register as sound. The sun's 5-minute oscillations correspond to a frequency of about 0.003 Hertz, far below what human ears can detect. But if you were to speed up these oscillations by a factor of about 42,000, they would become audible as a very low hum, like the lowest notes on an organ. Different parts of the sun resonate at different frequencies, creating a rich chord of overlapping tones that, if properly translated into the audible range, would produce a complex, ever-changing musical tone unique to our star. Other stars would sing different songs. A pulsating red giant, swelling and shrinking over days or weeks, would produce long, slow tones, perhaps like the deep resonance of a whale song. A rapidly pulsating white dwarf, vibrating every few seconds or minutes, would produce a higher-pitched sound. The most rapidly rotating pulsars, neutron stars that spin hundreds of times per second, would sing at pitches in the audible range if their rotation could somehow be converted to sound. The universe, if we could hear it, would be filled with music, each star a unique instrument, each galaxy an orchestra, all performing a grand cosmic symphony that has been playing for billions of years to an audience that, until recently, couldn't even imagine it existed. As you rest tonight, imagine that celestial music, that harmony of stellar vibrations and oscillations. Picture the sun humming its deep, complex chord. Imagine distant stars ringing like bells, pulsing like drums, resonating like strings. Though space carries no sound, the universe is far from silent. It vibrates with energy, oscillates with rhythm, glows with color, all of it information, all of it communication, stars speaking to us across the void in the only language available to them, light and mathematics and the fundamental laws of physics. And we improbably have learned to listen, to decode those messages, to understand what the stars are telling us. It's one of humanity's greatest achievements and a profound source of wonder. Star systems and cosmic companionship. Most stars are not solitary wanderers through the galaxy. Instead, the majority of stars exist in gravitationally bound systems with one or more companion stars, dancing together in intricate orbital patterns that can last for billions of years. There's something deeply comforting about these cosmic partnerships, These stellar relationships that endure across unimaginable spans of time, bound together by gravity's patient pull. Our Sun is unusual in being a single star, orbiting the galactic center alone except for its retinue of planets, asteroids, and comets. Most stars form in binary or multiple systems, where two or more stars orbit their common center of mass in stable, predictable patterns. These systems form when a molecular cloud fragments during collapse, creating multiple dense cores that each become a star, or when a rotating disk around a young star fragments and creates a companion. Once formed, if the stars are gravitationally bound to each other, they remain together indefinitely, barring an unlikely close encounter with another star. The closest star system to Earth, Alpha Centauri, is actually a triple star system. Alpha Centauri A and B are a binary pair, orbiting each other every 79.91 years at an average distance of about 23 astronomical units, a bit farther than the distance from the Sun to Uranus. Alpha Centauri A is slightly larger and hotter than the Sun, a G-type star similar to our own. Alpha Centauri B is a K-type star, smaller and cooler. They orbit each other in an elliptical orbit, sometimes approaching as close as 11 astronomical units, roughly the distance from the Sun to Saturn, and sometimes separating to 35 astronomical units beyond Neptune's orbit. Despite these changes in distance, their orbital dance is perfectly predictable, governed by Newton's laws of motion and gravity, repeating the same pattern they've followed for billions of years and will continue to follow for billions more. Proxima Centauri, the closest individual star to Earth, is gravitationally bound to the Alpha Centauri pair but orbits at a much greater distance, about 13,000 astronomical units or 0.21 light-years from the central pair. At this distance, Proxima takes perhaps 550,000 years to complete one orbit around the Alpha Centauri system, though some uncertainty remains about its exact orbital parameters. Proxima is a tiny red dwarf, only about 1/8 the Sun's mass, emitting less than 1% of the Sun's luminosity, yet it will outlive both members of the Alpha Centauri pair, still shining steadily when they have long since evolved into white dwarfs. Binary star systems come in many varieties. Closed binaries have stars separated by only a few stellar radii, sometimes close enough that their outer atmospheres touch, exchanging mass in a complex gravitational ballet. These systems can have orbital periods measured in hours or days. Semi-detached binaries occur when one star expands into a red giant and fills its Roche lobe, the region where its gravity dominates. Material from this star flows onto its companion through an accretion disk, creating spectacular X-ray sources if the companion is a neutron star or black hole. Contact binaries have stars that actually touch, sharing a common envelope of gas. Their surfaces merge together even as their cores remain distinct. These systems look like peanuts or figure eights and can have orbital periods of less than a day. Wide binaries, like Alpha Centauri, have stars separated by tens or hundreds of astronomical units. Their orbital periods range from decades to millennia. Some systems are so wide that the stars are separated by tens of thousands of astronomical units, taking millions of years to orbit each other, bound by gravity's reach even across such vast distances. Multiple star systems can be even more complex. Triple star systems usually have a hierarchical structure, a close binary pair with a distant third companion orbiting both. Quadruple systems often consist of two binary pairs orbiting each other. The more stars in a system, the more complex the gravitational interactions become. Yet these systems remain stable over cosmic timescales. Castor, the second brightest star in Gemini, is actually a sextuple star system, 3 binary pairs, all orbiting their common center of mass. The 3 pairs are separated by thousands of astronomical units, taking tens of thousands of years to orbit each other. Yet they remain bound together, a family of 6 stars slowly wheeling through space. There's remarkable stability in these systems. Once established, orbital configurations tend to persist indefinitely unless disturbed by an external event. The stars may evolve, changing size and brightness as they age, but their orbits continue largely unaltered. When a star in a binary system expands into a red giant, its companion's orbit may change slightly due to mass loss, but the system remains bound. Even when one star explodes as a supernova, the companion often remains attached, though the system may receive a kick from asymmetric mass loss, giving the surviving star and remnant a high velocity through the galaxy. The longest period binaries have separation distances of tens of thousands of astronomical units and orbital periods of millions of years. A star in such a system might complete only a few dozen orbits during its entire main sequence lifetime. Yet even these tenuous systems persist because encounters with other stars are extraordinarily rare. Space is vast and empty. Stars are separated by light years. The odds of another star passing close enough to disrupt a wide binary are minuscule over timescales of billions of years. Planets can exist in binary star systems, and we've discovered many such planets. Some orbit close to one star in a binary pair, far enough from the companion star that its gravity doesn't perturb the planet's orbit. These are called S-type or circumstellar orbits. Other planets, called circumbinary or P-type planets, orbit both stars of a close binary pair, experiencing sunrises and sunsets featuring 2 suns, like the famous scenes from Star Wars. These planets can have stable orbits if they're far enough from the binary that the 2 stars act approximately like a single-point mass. The planet Kepler 16b orbits 2 stars that eclipse each other every 41 days, creating a mesmerizing celestial dance visible from the planet's surface, if anyone were there to watch. The gravitational interactions in multiple star systems create rhythms and patterns that recur with clockwork precision. In eclipsing binary systems, one star periodically passes in front of the other from our perspective, dimming the combined light of the system. These eclipses repeat with perfect regularity, the period determined by the star's orbital speeds and separations. Algol, the demon star in Perseus, is an eclipsing binary with a period of 2.867 days. Every 2.867 days, like clockwork, Algol dims as the dimmer star passes in front of the brighter primary, then brightens again when the eclipse ends. This has been happening for millions of years and will continue for millions more, a cosmic metronome ticking away in the constellation Perseus. Some binary stars are so close they raise tides on each other, just as the moon raises tides on Earth's oceans. These tidal forces can synchronize the stars' rotations to their orbital periods, so each star always presents the same face to its companion, locked in a permanent embrace. This tidal synchronization takes millions of years to achieve, but, once established, remains stable indefinitely. The stars become tidally distorted, pulled into slightly elliptical shapes by each other's gravity, their mutual tides a constant reminder of their gravitational bond. There's poetry in these stellar relationships, these partnerships that last for eons. Two stars, born from the same cloud, living their entire lives together, orbiting each other in a pattern set billions of years ago, destined to continue that dance until one or both die and perhaps even beyond. If one star becomes a white dwarf while the other is still alive, they continue orbiting each other, the white dwarf a pale ember circling its still luminous companion. If both become white dwarfs, they circle each other as slowly cooling spheres, gradually fading over trillions of years, their orbit perhaps the last remaining evidence of their existence. Some binary systems end more dramatically. If a white dwarf accretes material from a companion star, the material can accumulate on the white dwarf's surface until conditions become right for a thermonuclear explosion, a nova that blasts the accreted material back into space. This process can repeat multiple times, the system flaring up every few decades or centuries as material accumulates and ignites. In extreme cases, if enough material accumulates, the white dwarf can exceed the Chandrasekhar limit of 1.4 solar masses and collapse, triggering a Type Ia supernova that destroys the white dwarf entirely. The companion star, suddenly released from its gravitational bond, becomes a high-velocity runaway star, continuing through the galaxy alone, perhaps the only evidence that a binary system once existed there. Yet for every dramatic ending, there are countless binary systems quietly orbiting each other in peaceful stability. Most binaries simply persist, their orbital dance unchanging, a source of regularity and predictability in a changing universe. The stars age, evolve, change in size and temperature and luminosity, but they remain together, bound by gravity's patient grip, companions across cosmic time. As you drift toward sleep, imagine those binary pairs scattered across the galaxy. Picture Alpha Centauri A and B slowly orbiting each other, as they have for billions of years, as they will for billions more. Envision countless other pairs, some close enough to share atmospheres, some separated by light weeks but still bound together. Think of the triple systems, quadruple systems, the vast sextuple system of Castor, all maintaining their intricate orbital patterns through the ages. There's comfort in this stability, this proof that relationships can last, that things can remain bound together across unimaginable time, that the universe contains partnerships as enduring as any human can imagine and more so. The stars above are not lonely. They have each other, and they dance together in patterns of perfect mathematical grace, choreographed by gravity, performed across billions of years, a ballet of light and matter that continues in silence, beauty, and eternal patience. The vast distances and our perspective. To truly appreciate the tranquility of the cosmos, we must understand the sheer enormity of cosmic distances, the vast spaces between objects that give the universe its character of serene emptiness. Space is not crowded. It is not hurried. It is fundamentally defined by emptiness, by the enormous voids between the tiny specks of matter we call stars and planets and galaxies. The most common unit for measuring distances within our solar system is the astronomical unit, defined as the average distance between Earth and the Sun, about 150 million kilometers or 93 million miles. This is already a distance difficult for human minds to grasp. If you could drive a car at highway speeds, say 100 kilometers per hour, it would take you about 170 years of continuous driving to cover one astronomical unit. Light, traveling at its characteristic 300,000 kilometers per second, takes 8 minutes and 20 seconds to cross this distance. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun. The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object, has traveled for more than 46 years and is currently about 160 astronomical units from the Sun, finally entering interstellar space after crossing the heliopause, the boundary where the Sun's solar wind yields to the interstellar medium. Yet despite traveling for nearly half a century at roughly 17 kilometers per second, Voyager has barely begun its journey into the galaxy. The nearest star, Proxima Centauri, is 268,000 astronomical units away. At Voyager's current speed, it would take about 73,000 years to reach Proxima, if it were heading in that direction, which it isn't. This leads us to the light year, the distance light travels in 1 year, about 9.46 trillion kilometers or 63,000 astronomical units. A light year is so large that it makes the solar system seem tiny by comparison. The entire orbit of Neptune, spanning 60 astronomical units in diameter, fits comfortably within 0.001 light years. The Oort cloud, a hypothetical sphere of comets surrounding the solar system, extends perhaps 100,000 astronomical units from the Sun, about 1.6 light years. Beyond that lies interstellar space, vast and empty, stretching for light years until you encounter the next star. Stars in our neighborhood of the galaxy are typically separated by several light years. Proxima Centauri, our nearest neighbor, is 4.24 light-years distant. The next nearest stars, Barnard's Star and Wolf 359, are about 6 and 7.8 light-years away, respectively. Sirius, bright and prominent, sits 8.6 light-years from us. Within a sphere of 15 light-years centered on the Sun, there are only about 60 stars, and most of them are dim red dwarfs invisible to the naked eye. The volume of space is so great that on average, stars in our stellar neighborhood are separated by light years of emptiness. This means that if the Sun were the size of a period on this page, Proxima Centauri would be another period about 16 meters away, with mostly empty space between. The galaxy contains approximately 200 billion to 400 billion stars, yet they're so spread out that stars almost never collide. Even when two galaxies merge, passing through each other, their stars almost always miss each other entirely because space between stars is so vast compared to the stars' physical sizes. The Milky Way galaxy itself is about 100,000 light-years in diameter and perhaps 1,000 light-years thick in the disk where the Sun resides. The Sun orbits the galactic center at a distance of about 26,000 light-years, taking approximately 230 million years to complete one orbit. This means the Sun has orbited the galaxy roughly 20 times since it formed 4.6 billion years ago. The last time the Sun was at its current position in the galaxy, dinosaurs hadn't yet evolved. The next time it returns to this spot, humanity will likely be extinct or evolved into something unrecognizable, unless we've figured out how to transcend our biological limitations. Beyond the Milky Way, distances become even more staggering. The Andromeda Galaxy, our nearest large galactic neighbor, lies about 2.5 million light-years away. The light we see from Andromeda tonight left that galaxy when Homo habilis, one of the earliest members of the genus Homo, was crafting the first stone tools in Africa. Andromeda and the Milky Way are gradually approaching each other due to gravity and will merge in about 4 billion years, though stars from the two galaxies will almost certainly pass by each other without colliding due to the vast spaces between them. The local group, the cluster of galaxies including the Milky Way, Andromeda, and about 50 smaller galaxies, spans roughly 10 million light-years. The Virgo supercluster, the larger structure containing the local group, spans about 110 million light-years. The observable universe, the region of space from which light has had time to reach us since the Big Bang, extends about 46.5 billion light-years in all directions, giving it a diameter of 93 billion light-years. This distance is larger than 13.8 billion light-years, the age of the universe, because space itself has been expanding. Photons traveling toward us have been fighting against that expansion, and meanwhile, the source they left from has been receding due to cosmic expansion, resulting in the current distance being larger than the light travel time would suggest. At cosmic scales, distances are often measured in megaparsecs. Parsec equals 3.26 light-years, defined by the geometry of Earth's orbit and parallax measurements. A megaparsec is 1 million parsecs, or about 3.26 million light-years. The Virgo cluster, a concentration of about 1,500 galaxies, is approximately 17 megaparsecs away. The Coma cluster is about 100 megaparsecs distant. The cosmic microwave background radiation, the afterglow of the Big Bang itself, comes from a distance of about 4,200 megaparsecs or 13.8 billion light-years, though the matter that emitted that radiation is now about 46 billion light-years away due to cosmic expansion. These distances are so large that they induce a particular state of mind when contemplated seriously. The human brain did not evolve to comprehend such scales. We evolved to understand distances of meters to kilometers, the scales relevant to survival on the African savanna. Cosmic distances break our intuitive understanding of space. They're not merely large. They represent a qualitatively different kind of largeness, a scale where familiar concepts lose meaning. And this vastness creates profound tranquility. The universe is not a crowded place. It is mostly emptiness, vast and serene. The stars are so far apart that interactions between them are rare. Collisions are almost unheard of. Each star exists in its own bubble of space, separated from neighbors by incomprehensible distances, traveling through the galaxy largely unperturbed for billions of years. When you look up at the night sky, you're seeing stars scattered across thousands of light years, each one isolated in its local region of space, each one carrying on its life of fusion and radiation without influence from nearby stars. This isolation means stability. The sun's environment doesn't change much over time. The nearby stars remain nearby. The distant stars remain distant. The galaxy rotates with stately slowness, taking hundreds of millions of years for patterns to noticeably change. If you could see the galaxy from above, watching in time-lapse as millions of years passed in seconds, you'd see the spiral arms slowly revolving, stars orbiting the center like a slowly spinning whirlpool, but no individual star would visibly interact with another. They'd simply move past each other at distances of light years, gravitationally insignificant, ships passing in the cosmic night. For us on Earth, this vast scale means we exist in a pocket of stability. The sun will continue shining steadily for billions of years. The stars in our sky will remain in essentially the same positions for thousands of years, changing only slowly due to proper motion, their individual motions through the galaxy. No star will approach close enough to perturb Earth's orbit in any foreseeable time frame. We are safe in our little bubble of space, insulated by light years from anything that might disrupt us, protected by distance and emptiness. There's deep comfort in this. The universe is not threatening. It is not hostile. It is simply large and empty and indifferent, and that indifference is a kind of peace. The cosmos doesn't care about our worries or our troubles. Our entire planet is an infinitesimal speck in one galaxy among hundreds of billions, and all of human history, every war, every achievement, every person who has ever lived, has occurred on this tiny mote of dust suspended in vast emptiness. When you feel overwhelmed, when problems seem insurmountable, remember the scale of the cosmos. Your difficulties, as real as they are to you, don't even register at cosmic scales. The universe continues, patient and enormous, completely unaffected by whatever troubles you might face. This perspective doesn't diminish the importance of human life or human concerns. Instead, it places them in context. We matter to each other. We matter to ourselves. But we don't matter to the universe, and there's freedom in that realization. There's no cosmic judgment, no universal significance that we must live up to. We're free to find our own meaning, create our own purposes, define our own values, all while floating through space on a little world, surrounded by mostly nothing, accompanied at vast distances by countless other stars, each one minding its own business, each one simply existing, as we exist, as temporary patterns of matter and energy in an enormous universe that has plenty of room for all of us and more. As sleep approaches, let yourself feel small in a good way. You are tiny. Your world is tiny, but teeniness is not insignificance. It is liberation. You don't have to carry the weight of the cosmos. You can simply be here, now, in this moment, while light years away, stars continue their slow journeys through the galaxy, separated by distances that make human scales irrelevant, creating a universe that is vast, empty, peaceful, and utterly, wonderfully indifferent to everything except the basic laws of physics that govern us all equally, stars and humans alike, matter and energy, all existing together in this enormous space, all temporary, all brief, all part of the same cosmic story that's been unfolding for 13.8 billion years and will continue for billions or trillions more, long after we're gone, long after our sun has died, long after our galaxy has merged with others, the universe simply continuing, as it always has, patient and vast and deeply, profoundly calm. Stellar nurseries and cosmic gardens. The regions where stars are born are among the most beautiful and serene locations in the galaxy. These stellar nurseries, vast clouds of molecular hydrogen and dust, drift through space like cosmic gardens, slowly sculpting new stars from the raw material of the interstellar medium. To understand these places is to witness creation occurring on timescales so extended that it seems less like an event and more like a gentle, ongoing process, as natural and unhurried as growth itself. Molecular clouds are the largest objects in the galaxy, some spanning hundreds of light years across and containing enough mass to form hundreds of thousands of stars. The Orion Molecular Cloud Complex, one of the nearest large star-forming regions at about 1,500 light-years from Earth, contains enough material to create about 2 million stars the size of our Sun. This cloud has been forming stars for millions of years and will continue for millions more, gradually converting its gas into stellar systems while new material from the interstellar medium replenishes what's been lost. These clouds are cold, typically only 10 to 20 degrees above absolute zero, about minus 260 degrees Celsius. At such temperatures, almost all molecules slow down dramatically, their thermal motion minimal. Hydrogen, the dominant component, exists primarily as molecular H2, two hydrogen atoms bonded together. This molecular hydrogen makes up about 70% of the cloud's mass. The remaining 30% is mostly helium, with trace amounts of heavier elements like carbon, nitrogen, and oxygen, which form molecules like carbon monoxide, ammonia, water ice, and complex organic compounds. The clouds are also dark. Dust grains, tiny particles of silicon, carbon, and ice, only about 1 micrometer in size, block visible light from background stars, creating dark patches in the sky where these clouds reside. The Horsehead Nebula, a famous dark nebula visible in silhouette against brighter gas behind it, is a perfect example. It's a dense pillar of gas and dust, gradually being eroded by intense radiation from nearby bright stars, creating its distinctive horsehead shape. Within this pillar, new stars are forming, hidden from visible light but detectable in infrared wavelengths that can penetrate the dust. Inside molecular clouds, the density is remarkably low by terrestrial standards, typically a few thousand to a few million molecules per cubic centimeter. For comparison, air at sea level contains about 25 quintillion molecules per cubic centimeter. Yet despite this extreme tenuousness, over volumes of cubic light years, these clouds accumulate tremendous mass. The Orion molecular cloud contains roughly 2 million solar masses of material, compressed into a region about 200 light-years across. Within the cloud, denser regions called molecular cloud cores serve as the sites where individual stars form. These cores might be only a light-year or so across but contain 10 to perhaps 1,000 solar masses of material. Gravity slowly pulls material toward the center of the core, compressing it. The process takes about 1 million years, a geological timescale, profoundly rapid by cosmic standards but still long enough that no human observer could watch it happen in real time. As material falls inward, it heats up due to compression and friction. The center becomes warmer and denser. A protostar forms, a glowing ball of gas not yet hot enough for fusion but radiating energy from gravitational contraction. Around the protostar, a disk of gas and dust forms, called a protoplanetary disk or accretion disk. This disk is where planets will eventually form, coalescing from dust grains that stick together, gradually building up larger and larger bodies through gentle collisions over millions of years. The protostar continues to grow by accreting material from the disk and from infalling gas. Magnetic fields channel some of the inflowing material into jets that shoot out perpendicular to the disk at speeds of hundreds of kilometers per second. These jets, called Herbig-Haro objects when they slam into surrounding gas and create glowing shock waves, are among the most dramatic features of star formation. They carve out cavities in the surrounding cloud, clearing space for the new star and redistributing material across light years. Not all material in the cloud forms stars. Most of it is either dispersed back into the interstellar medium by stellar winds and radiation from the newly formed stars or remains as remnants of the protoplanetary disk, potentially forming planets, asteroids, and comets. The efficiency of star formation is surprisingly low. Typically, only a few % of a cloud's mass ends up in stars. The rest is recycled, waiting to participate in future generations of star birth. Famous star-forming regions visible from Earth include the Orion Nebula, the Carina Nebula, the Eagle Nebula, and the Lagoon Nebula. The Orion Nebula, also known as M42, is a glowing gas cloud visible to the naked eye as the middle star in Orion's sword. It's actually a massive stellar nursery where thousands of young stars are being born. At its heart lies the trapezium cluster, for massive young stars whose intense ultraviolet radiation ionizes the surrounding gas, causing it to glow brilliantly. These stars formed only about 2 million years ago, making them infants by stellar standards. The Eagle Nebula, located about 7,000 light-years away, contains the famous pillars of creation, dense columns of gas and dust captured in a stunning image by the Hubble Space Telescope. These pillars are being eroded by ultraviolet light from nearby hot stars, gradually boiling away, but within them, new stars are gestating, protected by the dense material until they're ready to emerge. The largest pillar is about 4 light-years tall, meaning light takes 4 years to travel from its base to its tip. The Carina Nebula, one of the largest and brightest nebulae in the sky, lies about 7,500 light-years away and contains numerous stellar nurseries. It's home to Eta Carinae, one of the most massive and luminous stars in the galaxy, a blue supergiant that may explode as a supernova anytime within the next million years. The nebula also contains dark molecular clouds where star formation continues, creating clusters of young, hot stars that illuminate the surrounding gas with their intense radiation. The predictability of stellar behavior. There's something profoundly comforting about understanding that stars, despite being immense spheres of blazing plasma scattered across unimaginable distances, follow rules we can comprehend. They obey laws, maintain equilibrium, and exhibit patterns that humans, dwelling on a small blue world, have managed to decode through careful observation and mathematical reasoning. In the grand cosmic order, stars represent one of the universe's most reassuring demonstrations of predictability, a testament to the fundamental consistency of physical laws wherever they apply. Let's begin by contemplating the sheer elegance of this truth. When you look up at the night sky, you're witnessing the product of mathematical principles that govern not just the stars you see, but every star in every galaxy throughout the observable universe. The same equations that describe the behavior of a red dwarf burning dimly in a distant spiral arm also apply to the brilliant blue giants anchoring stellar nurseries thousands of light-years away. This universality isn't just convenient for astronomers. It's one of the most remarkable discoveries in all of human history. It tells us that the cosmos operates under a consistent set of rules, that nature plays the same game everywhere, using the same fundamental playbook. The laws of physics that govern stars are neither arbitrary nor capricious. They emerge from the basic properties of matter and energy, from the way particles interact under the influence of fundamental forces. Gravity, the weakest of the 4 fundamental forces, yet the one that sculpts the large-scale structure of the universe, provides the inward pull that attempts to compress stellar material into an ever smaller volume. Meanwhile, the pressure generated by the incredible temperatures and densities within a star pushes outward, resisting gravity's inexorable squeeze. These two opposing forces engage in a precise balancing act that lasts for millions or even billions of years, a stellar equilibrium so stable that our own sun has maintained it for roughly 4.5 billion years with barely a fluctuation. This balance, known as hydrostatic equilibrium, forms the foundation of stellar stability. Picture, if you will, a star as a collection of nested spherical shells, each one pressing down upon those below it with the full weight of all the material above. In any given layer of the star, the pressure must be exactly sufficient to support the weight of everything overhead. If the pressure were too low, that layer would collapse under the burden. If the pressure were too high, it would expand outward, pushing the overlying material away. But in a stable star, the pressure is just right, creating a perfect balance at every single depth from the surface down to the core. What generates this pressure? The answer lies in the fundamental nature of gases and the extraordinary temperatures that prevail within stellar interiors. At the core of a star like our Sun, temperatures soar to approximately 15 million degrees Kelvin. At such temperatures, matter exists in a state called plasma, where electrons are stripped from their atomic nuclei, creating a seething soup of charged particles all moving at tremendous speeds. These particles constantly collide with one another, and each collision represents a transfer of momentum, a tiny push. When billions upon billions upon billions of such collisions occur every instant, the cumulative effect is pressure, an outward force that can counteract the inward pull of gravity even when dealing with stellar masses. The relationship between temperature, density, and pressure in stellar interiors follows the ideal gas law, a deceptively simple equation that encapsulates profound truths about how matter behaves. This law states that pressure is directly proportional to both temperature and density. Heat up a gas and its pressure increases. Compress it and its pressure increases. Cool it down or allow it to expand, and the pressure decreases accordingly. Stars, despite their exotic nature, obey this familiar principle, the same one that explains why a tire inflates when you pump air into it or why a balloon expands when you heat it. Within the core of a star, nuclear fusion provides the heat source that maintains the high temperatures necessary for hydrostatic equilibrium. Hydrogen nuclei, stripped of their electrons and moving at colossal velocities, occasionally collide with sufficient force to overcome their mutual electrical repulsion. When this happens, they fuse together to form helium, releasing a burst of energy in the process. This energy, initially in the form of high-energy gamma-ray photons, works its way outward through the star over the course of hundreds of thousands to millions of years, gradually heating each successive layer and maintaining the temperature gradient that supports the structure. The sensitivity of nuclear fusion to temperature creates a remarkable self-regulating system, a stellar thermostat that keeps fusion rates stable over vast stretches of time. If, for some reason, the fusion rate in a star's core were to increase slightly, the additional energy released would raise the temperature. The increased temperature would cause the gas pressure to rise, which would make the core expand. As the core expanded, its density would decrease, and the lower density would reduce the rate of nuclear collisions, bringing the fusion rate back down. Conversely, if the fusion rate decreased, the core would cool slightly, pressure would drop, gravity would compress the core, density would increase, and the fusion rate would climb back up. This negative feedback loop acts like a highly sensitive control system, automatically adjusting the energy production to maintain equilibrium. The mathematical description of stellar structure rests on a foundation of equations that relate fundamental stellar properties to one another. These equations describe how mass is distributed throughout a star's interior, how pressure varies with depth, how temperature changes from layer to layer, and how energy flows from the core to the surface. When solved simultaneously for stars of different masses and compositions, these equations predict the full range of stellar properties we observe. Their luminosities, surface temperatures, radii, and lifetimes. One of the most important relationships emerging from these equations is the mass-luminosity relation, which reveals that a star's brightness is intimately connected to how much mass it contains. More massive stars are dramatically more luminous than their less massive cousins, not because they're merely proportionally brighter, but because luminosity scales roughly as mass raised to the power of 3.5. Double a star's mass and you don't just double its luminosity, you increase it by a factor of more than 11. Increase the mass by a factor of 10 and the luminosity explodes by more than 3,000 times. This steep relationship exists because more massive stars require higher core temperatures and pressures to maintain hydrostatic equilibrium against their stronger gravitational fields. The greater gravitational compression in a massive star's core produces higher densities and temperatures, and the nuclear fusion rate is exquisitely sensitive to temperature. Even a modest increase in core temperature causes the fusion rate to skyrocket, pumping out vastly more energy. This is why the most massive stars, despite having much larger fuel reserves than smaller stars, burn through their hydrogen supplies far more quickly. A star with 80 times the Sun's mass might exhaust its core hydrogen in just a few million years, whereas a star with 1/10 the Sun's mass could sustain fusion for trillions of years, far longer than the current age of the universe. The Stefan-Boltzmann law provides another crucial piece of the stellar puzzle, connecting a star's luminosity to its radius and surface temperature. This law states that the total energy radiated by a star each second is proportional to the square of its radius and the fourth power of its surface temperature. A star's surface temperature determines not only how much energy each square meter of its photosphere emits, but also the color of its light. Hot stars with surface temperatures of 30,000 Kelvin or more glow with a fierce blue-white radiance, while cooler stars with temperatures around 3,000 Kelvin emit a ruddy red glow. The Stefan-Boltzmann law helps explain one of the more counterintuitive aspects of stellar astronomy: the existence of stars that are simultaneously cool and incredibly luminous, or hot yet remarkably dim. A red giant star like Betelgeuse, with a surface temperature of only about 3,500 Kelvin, nevertheless shines with the light of tens of thousands of suns because it has swollen to an enormous size, with a radius hundreds of times greater than our sun's. Each square meter of its surface might emit less light than an equivalent area on the sun, but Betelgeuse has so much more surface area that its total luminosity becomes staggering. Conversely, a white dwarf star might have a surface temperature of 10,000 Kelvin or higher, yet shine with only a fraction of the sun's luminosity because it has compressed down to roughly the size of Earth, giving it relatively little surface area from which to radiate. These relationships between mass, luminosity, temperature, and radius aren't arbitrary correlations noticed by chance. They emerge naturally from the physical processes occurring within stars, from the interplay between gravity, pressure, temperature, and nuclear physics. When astronomers construct mathematical models of stellar interiors, incorporating our understanding of how matter behaves under extreme conditions, these relationships fall out of the equations as inevitable consequences. The models predict stellar properties that match, often with remarkable precision, what we observe when we point our telescopes at actual stars. This predictive power extends beyond individual stars to entire stellar populations. When we examine star clusters, groups of thousands or even millions of stars that formed at roughly the same time from the same cloud of gas and dust, we can trace out their collective properties on what's called a Hertzsprung-Russell diagram. This diagram, plotting stellar luminosity against surface temperature, reveals clear patterns that reflect the underlying physics governing stellar evolution. The vast majority of stars in a young cluster fall along a diagonal band called the main sequence, where stars spend most of their lives steadily fusing hydrogen into helium. Their positions along this band are determined primarily by their masses, with the most massive, hottest, and most luminous stars anchoring the upper left while the least massive, coolest, and dimmest stars define the lower right. As a cluster ages, the most massive stars, which burn through their fuel most rapidly, exhaust their core hydrogen first and begin to evolve away from the main sequence. They swell into red giants, dramatically increasing their luminosity as their outer layers expand while their cores contract and heat up. This evolution traces out predictable paths on the Hertzsprung-Russell diagram, paths that depend on the star's initial mass and the time that has elapsed since its formation. By examining where stars in a cluster have begun to leave the main sequence, astronomers can determine the cluster's age with considerable accuracy. A cluster where only stars more massive than 20 solar masses have evolved away from the main sequence must be quite young, only a few million years old. A cluster where stars comparable to the Sun are beginning to evolve must be several billion years old, approaching the current age of our own Sun. The classification of stars into spectral types represents another manifestation of stellar predictability. When astronomers first began systematically studying stellar spectra in the late 19th and early 20th centuries, they noticed that stars could be arranged into a sequence based on the absorption lines visible in their light. Initially classified alphabetically based on the strength of hydrogen lines, the classification was later reordered to reflect surface temperature, yielding the familiar sequence O, B, A, F, G, K, M, running from hottest to coolest. Each spectral class can be further subdivided into 10 subtypes, creating a fine-grained classification scheme that allows astronomers to place any star along this temperature sequence with considerable precision. This classification system works because stellar spectra are determined primarily by surface temperature, which governs which elements can exist in which ionization states in a star's photosphere and thus which absorption lines appear in the spectrum. The hottest O-type stars, with surface temperatures above 30,000 Kelvin, show strong ionized helium lines and weak hydrogen lines because temperatures are so high that most hydrogen atoms have been ionized, stripping them of their electrons and preventing them from absorbing light at the wavelengths characteristic of hydrogen. Cooler A-type stars, with surface temperatures around 10,000 Kelvin, show the strongest hydrogen lines because temperatures are in the sweet spot where many hydrogen atoms retain their electrons but are energetically excited enough to absorb light efficiently. Even cooler M-type stars, with temperatures below 4,000 Kelvin, show complex spectra dominated by molecular absorption bands from molecules like titanium oxide, which can exist in the relatively mild conditions of these stars' atmospheres. This spectral sequence is a temperature sequence, and since surface temperature correlates with many other stellar properties through the physical laws governing stellar structure, spectral type tells us far more than just how hot a star's surface is. It provides clues about the star's mass, luminosity, radius, and evolutionary state. An O-type star on the main sequence must be very massive, typically more than 16 times the Sun's mass, extraordinarily luminous and comparatively young, because such massive stars have main sequence lifetimes of only a few million years. A G-type star like our Sun occupies the middle ground with moderate mass, luminosity, and a main sequence lifetime of about 10 billion years. An M-type star on the main sequence must be a lightweight, typically less than half the Sun's mass, dim, cool, and capable of shining for hundreds of billions of years before exhausting its hydrogen fuel. Adding to the classification scheme is the luminosity class, denoted by Roman numerals, which distinguishes between stars of the same temperature but different luminosities and sizes. A G2V star like our Sun is a main sequence dwarf, fusing hydrogen in its core and maintaining the standard relationship between mass, luminosity, and temperature. A G23 star would be a giant, a star that has exhausted its core hydrogen and swollen to many times its former size, becoming far more luminous despite having the same surface temperature. A G2I star would be a supergiant, even larger and more luminous still. These luminosity classes reflect different evolutionary stages and internal structures, but they too follow predictable patterns determined by stellar mass and the physical processes occurring within the star. The predictability extends even to the relatively rare and exotic classes of stars that deviate from the main patterns. Wolf-Rayet stars, massive objects that have lost their outer hydrogen envelopes through powerful stellar winds, exhibit emission lines in their spectra rather than the usual absorption lines, but their properties still conform to physical principles. Their extreme temperatures and luminosities reflect the fact that we're seeing deep into what were once their interiors, regions where nuclear fusion has produced heavier elements and where temperatures soar to well over 50,000 Kelvin. Carbon stars, cool giants rich in carbon rather than oxygen, show molecular absorption bands from carbon-bearing molecules, but this too is predictable given the nuclear processes that enriched their atmospheres with carbon dredged up from deep within their interiors. Kepler's laws of planetary motion, first derived empirically from observations of planets orbiting the Sun, turn out to apply to binary star systems as well. When two stars orbit their common center of mass, their orbital periods, orbital sizes, and masses are related by precisely the same mathematical relationships that govern planetary orbits. This universality allowed astronomers to determine stellar masses by carefully observing binary systems, measuring the stars' orbital periods and separations, and then applying Kepler's third law, generalized by Isaac Newton, to account for the masses of the orbiting bodies. These measurements confirmed the theoretical predictions of stellar models, revealing that main sequence stars indeed follow the expected mass-luminosity relationship and providing crucial calibration data that strengthen confidence in our understanding of stellar physics. Newton's law of universal gravitation itself is central to stellar structure, providing the mathematical description of the force that holds stars together and drives their evolution. Every particle of matter in a star attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. When you integrate this force over all the matter in a star, you obtain the gravitational pressure gradient that must be balanced by thermal pressure to maintain hydrostatic equilibrium. The mathematical elegance of Newton's law, with its simple inverse square dependence on distance, underpins much of astrophysics and allows us to make precise predictions about stellar behavior. Einstein's theory of general relativity, which superseded Newtonian gravity for the most extreme conditions, predicts that gravity itself arises from the curvature of spacetime caused by the presence of mass and energy. For most stars, relativistic corrections to Newtonian gravity are small, but for the most compact stellar remnants, white dwarfs and neutron stars, general relativity becomes essential for accurate calculations. Even in these exotic objects, however, the behavior remains predictable, governed by equations that relate mass, radius, and the equation of state of matter at densities far exceeding anything achievable in terrestrial laboratories. The reliability of stellar physics rests on our understanding of how matter behaves under the conditions found in stellar interiors. The equation of state, which relates pressure, temperature, and density, has been tested extensively through laboratory experiments and theoretical calculations. For ordinary matter in the form of an ideal gas, the relationship is simple and well established. For matter under more extreme conditions, such as the electron-degenerate matter in white dwarfs or the neutron-degenerate matter in neutron stars, the equation of state becomes more complex, incorporating quantum mechanical effects that become important when particles are squeezed into tiny volumes. Yet even these exotic states of matter obey physical laws we can describe mathematically, allowing us to predict their properties and the behavior of objects composed of them. Nuclear physics provides the other essential ingredient for understanding stellar behavior. The rates of fusion reactions depend on the energies of colliding nuclei, which in turn depend on temperature, and on the cross-sections for nuclear interactions, which have been measured in laboratory experiments or calculated using quantum mechanics. The proton-proton chain that powers stars like the Sun proceeds through a series of well-understood steps, each with its own characteristic rate. More massive stars employ the CNO cycle, where carbon, nitrogen, and oxygen nuclei act as catalysts for hydrogen fusion, and this process too has been thoroughly studied. The sensitivity of these fusion rates to temperature, with the CNO cycle showing an especially steep temperature dependence, explains the self-regulating nature of stellar cores and the dramatic differences in main sequence lifetimes between stars of different masses. Opacity, the property that describes how easily photons can travel through stellar matter, also follows physical principles that can be calculated from atomic physics. When photons interact with matter, they can be absorbed by atoms and molecules, scattered by electrons, or blocked by bound-free and free-free processes where electrons transition between bound atomic states and free motion. Each of these processes has a characteristic dependence on temperature, density, and chemical composition, and their combined effect determines how long it takes for energy to diffuse from a star's core to its surface. This in turn affects the star's radius and luminosity, tying together disparate stellar properties through a web of physical relationships. As photons work their way from the core toward the surface, they gradually shift from high-energy gamma rays to visible light, transferring energy to the surrounding matter in countless interactions. In the radiative zones of stars, energy transport occurs primarily through this radiative diffusion, with photons taking a random walk through the stellar interior, absorbed and re-emitted countless times before finally escaping into space. In convective zones, where the temperature gradient is steep enough, energy transport shifts to convection, with hot plasma rising toward the surface, cooling, and sinking back down in vast circulating currents. Whether a region is radiative or convective depends on the temperature gradient and the opacity of the material, both of which can be calculated from physical principles, allowing stellar models to predict the internal structure of stars with considerable accuracy. The predictability of stellar behavior extends to stellar evolution as well. As stars age, they undergo changes that follow well-defined pathways determined primarily by their initial masses. A star like the Sun will spend about 10 billion years on the main sequence, fusing hydrogen in its core. When the core hydrogen is exhausted, the core will contract and heat up while the outer layers expand, transforming the Sun into a red giant. Helium fusion will then ignite in the core, sustaining the star for another 100 million years or so before that fuel too is exhausted. The Sun will then shed its outer layers in a planetary nebula, leaving behind a white dwarf that will gradually cool over trillions of years. Each of these stages, from main sequence to red giant to planetary nebula to white dwarf, follows patterns that stellar evolution theory can predict based on the initial mass and composition of the star. More massive stars follow different evolutionary paths, but ones that are no less predictable. A star with 20 times the Sun's mass will speed through its main sequence life in just a few million years, burning hydrogen at a prodigious rate. It will swell into a supergiant, fusing progressively heavier elements in its core in a series of stages that culminate in the production of iron. When the core reaches a mass of about 1.5 solar masses and can no longer generate energy through fusion, it will collapse catastrophically in less than a second, rebounding in a supernova explosion that briefly outshines an entire galaxy. The core may survive as a neutron star or, if the progenitor star was massive enough, as a black hole. Each of these outcomes is predictable based on the star's initial mass and the laws of physics governing stellar structure and evolution. Even the most violent stellar phenomena, supernovae, follow patterns we can understand. Type II supernovae result from the core collapse of massive stars that have retained their hydrogen envelopes. Type I supernovae come in several flavors, with Type Ia resulting from the thermonuclear explosion of a white dwarf that has accreted enough mass from a companion star to exceed the Chandrasekhar limit, the maximum mass that electron degeneracy pressure can support. The light curves of these explosions, the way their brightness changes over time, reflect the radioactive decay of unstable isotopes produced in the explosion, and these decay rates are known from nuclear physics. By comparing observed supernova light curves to theoretical models, astronomers can determine distances to remote galaxies and study the expansion history of the universe. The consistency of physical laws across the universe means that we can study stars in distant galaxies and know that they obey the same rules as stars in our own Milky Way. When we observe the spectra of stars in a galaxy millions of light-years away, we see the same absorption lines, shifted to longer wavelengths by the galaxy's recession velocity but otherwise identical to the spectra of nearby stars of the same type. When we measure the colors and magnitudes of stars in remote stellar clusters, they fall into the same patterns on the Hertzsprung-Russell diagram, tracing out main sequences and giant branches that match theoretical predictions. This universality provides strong evidence that our understanding of stellar physics is fundamentally sound, not limited to our local cosmic neighborhood but applicable throughout the observable universe. The predictability of stellar behavior offers more than just intellectual satisfaction or practical utility for astronomers. It speaks to something deeper about the nature of reality itself. We live in a universe that operates according to mathematical laws, laws that we can discover through observation and experiment, express in the language of mathematics, and use to make predictions about phenomena far beyond our direct experience. Stars, despite being almost incomprehensibly large and remote, are not inscrutable mysteries. They are natural objects governed by physics, objects we can study, understand, and whose behavior we can anticipate with remarkable accuracy. There's a meditative quality to contemplating this predictability, a sense of cosmic order that can be deeply reassuring. In a world that often feels chaotic and uncertain, where human affairs are subject to countless unpredictable influences, and where chance seems to play such a large role, the stars shine with a constancy grounded in physical law. They don't change their behavior on a whim. They don't violate the principles that govern their existence. A star will not suddenly decide to burn its fuel differently or ignore the force of gravity. It simply is what it is, following the path laid out by its mass and composition, evolving according to timescales and processes we can calculate and predict. This reliability has practical importance as well. Astronomers use our understanding of stellar physics to estimate the ages of star clusters, providing constraints on the age of the universe itself. By comparing theoretical stellar evolution models to observations of the oldest globular clusters, clusters of hundreds of thousands of stars that formed in the early universe, astronomers can infer that these clusters are about 13 billion years old, consistent with other estimates of the universe's age from cosmology. The fact that multiple independent methods yield consistent ages strengthens our confidence in both stellar evolution theory and cosmological models. Stellar physics also helps us understand the origin of the chemical elements that make up planets and life itself. Stars are cosmic furnaces where hydrogen and helium, the primordial elements created in the Big Bang, are transformed into heavier elements through nuclear fusion. Carbon, nitrogen, oxygen, silicon, iron, and all the elements up to iron are synthesized in the cores of stars through fusion reactions, while elements heavier than iron are created in the extreme conditions of supernova explosions and neutron star mergers. When massive stars explode or when white dwarfs detonate in thermonuclear supernovae, they scatter these newly forged elements into space, enriching the interstellar medium with the raw materials for new generations of stars and planetary systems. Our own bodies are made of atoms that were created in the hearts of stars that lived and died billions of years ago, a poetic truth that rests on the solid foundation of stellar physics. The predictability of stars allows us to use them as standard candles for measuring cosmic distances. Certain types of stars, particularly Cepheid variables, pulsate with periods that are tightly correlated with their intrinsic luminosities. By measuring a Cepheid's pulsation period, we can determine how luminous it truly is, and by comparing this intrinsic luminosity to how bright the star appears from Earth, we can calculate its distance. This technique, along with others based on stellar physics, has allowed astronomers to map out the scale of the universe, determining the distances to nearby galaxies and establishing the cosmic distance ladder that extends from our local neighborhood to the edge of the observable universe. Type 1a supernovae serve as even more powerful standard candles because they are so luminous that they can be seen at immense distances. These explosions, resulting from white dwarfs reaching a critical mass limit, have remarkably consistent peak luminosities, making them excellent distance indicators. Observations of Type 1a supernovae in distant galaxies led to the discovery that the expansion of the universe is accelerating, a profound finding that suggests the existence of dark energy, a mysterious component that makes up about 70% of the universe's total energy density. This discovery, honored with the 2011 Nobel Prize in Physics, rests on our understanding of stellar evolution and the predictable properties of white dwarf supernovae. The study of stellar oscillations, or astroseismology, pushes our understanding of stellar interiors to new levels of detail. Just as geologists use seismic waves to probe Earth's interior structure, astronomers use the oscillations of stars to learn about conditions deep within them. Stars can vibrate in various modes, with their surfaces rising and falling in complex patterns driven by internal sound waves or gravity waves. The frequencies of these oscillations depend on the star's internal structure, particularly the density, temperature, and composition profiles. By measuring oscillation frequencies with high precision and comparing them to theoretical models, astronomers can test stellar physics in unprecedented detail, checking whether our equations of state, opacities, and energy generation rates accurately describe conditions inside actual stars. Our Sun, being the nearest star and by far the easiest to study in detail, provides the best laboratory for testing stellar models. Helioseismology, the study of solar oscillations, has revealed the Sun's internal rotation profile, showing that the core rotates at a different rate than the surface, and has helped refine our understanding of the solar interior. Neutrinos from nuclear reactions in the Sun's core stream through space in all directions, and detectors on Earth can capture a tiny fraction of them, providing direct information about fusion rates deep in the solar core. For decades, measurements detected fewer solar neutrinos than theory predicted, creating the so-called solar neutrino problem. The resolution came not from modifications to stellar models but from particle physics. Neutrinos can oscillate between different types, and some of the electron neutrinos produced in the Sun convert to other neutrino types that early detectors couldn't observe. This discovery confirmed both stellar models and new physics beyond the standard model of particle physics, demonstrating how stellar astronomy and fundamental physics inform each other. The predictability of stellar behavior means that when we observe something unexpected, we know we've encountered something genuinely interesting, a phenomenon that demands explanation. When astronomers discovered stars whose brightness varies in regular patterns but not for reasons explained by normal stellar evolution, detailed study revealed new physical processes. Cepheid variables pulsate because they lie in a region of the Hertzsprung-Russell diagram where a star's opacity changes dramatically with temperature, creating a valve mechanism that drives oscillations. RR Lyrae stars pulsate for similar reasons but occupy a different region of the diagram and have different masses and evolutionary histories. These discoveries extended our understanding of stellar physics without overturning the fundamental principles. When astronomers find stars that seem to violate normal patterns, closer examination usually reveals that they're either unusual systems where special circumstances apply or that we're misinterpreting the observations. Blue stragglers, anomalously blue stars found in old stellar clusters where all such massive, luminous stars should have already evolved away from the main sequence, puzzled astronomers for years until it was realized that they likely result from stellar mergers or mass transfer in binary systems. These processes inject new life into what would otherwise be aging stars, explaining the apparent anomaly through mechanisms consistent with stellar physics rather than requiring new laws. The predictability of stars means we can simulate their evolution in computers, constructing detailed models that follow a star from birth to death. These stellar evolution codes incorporate the equations of stellar structure, nuclear reaction networks that track the burning of various fuels, and sophisticated treatments of energy transport and opacity. By running such simulations for stars of different masses and compositions, astronomers have created grids of stellar models that span the full range of stellar properties observed in the universe. These models predict not just the main sequence lifetimes and evolutionary endpoints, but also the detailed paths stars follow on the Hertzsprung-Russell diagram, the changes in their surface compositions as nuclear burning products are mixed to the surface, and the types of remnants they leave behind. Advances in computing power have allowed stellar models to become increasingly sophisticated, incorporating three-dimensional simulations of convection zones, detailed treatments of rotation and magnetic fields, and realistic models of mass loss through stellar winds. These refinements have improved the match between theoretical predictions and observations, giving us confidence that we truly understand the fundamental processes governing stellar behavior. When models and observations disagree, as they sometimes do in subtle ways, the discrepancies point to areas where our understanding can be improved, where additional physics needs to be included, or where uncertainties in input parameters need to be reduced. Binary stars provide particularly stringent tests of stellar models because both stars in a system formed at the same time from the same material and are at the same distance from us. This removes several sources of uncertainty, allowing for more direct comparisons between theory and observation. Eclipsing binary systems are especially valuable because, by observing how the brightness changes as one star passes in front of the other, astronomers can determine the star's sizes, shapes, and surface brightness distributions with remarkable precision. The masses can be determined from the orbital motions, and with accurate masses, sizes, and luminosities in hand, these systems provide crucial calibration data that test theoretical models in detail. The predictability extends even to the remnants of stellar evolution. White dwarfs, the cooling embers of low and intermediate mass stars, settle into a state where electron degeneracy pressure supports them against gravity. This quantum mechanical pressure, arising from the Pauli exclusion principle that prevents electrons from occupying the same quantum state, depends only on density, not on temperature. As a result, white dwarfs cool gradually over billions of years, radiating away their residual thermal energy without shrinking. The cooling rate depends on their initial temperatures and compositions, but it's entirely predictable from physics, allowing astronomers to use white dwarf cooling sequences to estimate the ages of stellar populations. Neutron stars, the remnants of massive stars that exploded as supernovae, are even more exotic, supported by neutron degeneracy pressure and reaching densities where atomic nuclei merge into a neutron-rich soup. These objects test physics under extreme conditions, where densities exceed those in atomic nuclei and where general relativistic effects become important. Yet they too obey physical laws we can describe, if imperfectly given the uncertainties in the equation of state of matter at such densities. Neutron stars have been observed as pulsars, rapidly spinning objects that emit beams of radio waves, and their properties match theoretical predictions reasonably well, though mysteries remain about their internal structure and the behavior of matter at nuclear densities. Black holes, the ultimate stellar remnants, result when a core collapses beyond the point where even neutron degeneracy pressure can halt it. These objects are described by Einstein's general theory of relativity, with their properties determined entirely by their mass, spin, and electric charge according to the no-hair theorem. They warp spacetime so severely that not even light can escape from within their event horizons, but their existence and basic properties are predicted by a theory developed over a century ago, a theory that continues to pass every experimental and observational test we can devise. The predictability of stellar behavior reflects something profound about the universe we inhabit. It's a universe where matter and energy interact according to consistent rules that are comprehensible to minds like ours, rules that can be discovered through patient observation and careful reasoning. This comprehensibility is not something we should take for granted. One could imagine a universe where physical laws changed from place to place or from time to time, where the same experiment produced different results depending on circumstances we couldn't predict or control. Such a universe would be fundamentally less knowable than our own. The fact that stars billions of light years away obey the same laws as stars in our galactic neighborhood and that they presumably obeyed those same laws billions of years ago when the light we now see from them began its journey, suggests a deep constancy in nature that makes science possible. As you reflect on these truths, consider the journey of understanding that brought us here. For most of human history, stars were mysteries, lights in the sky whose nature and behavior were utterly unknown. Ancient peoples wove stories around the constellations, attributing the motions of celestial objects to the actions of gods or spirits. Even as astronomy developed into a more systematic science, stars remained beyond direct investigation, their distances so vast that they appeared as mere points of light in even the most powerful telescopes. Yet through spectroscopy, the study of how stars absorb and emit light at different wavelengths, astronomers found a way to probe stellar properties in extraordinary detail. The pattern of absorption lines in a star's spectrum reveals its temperature, composition, and motion through space. The width of spectral lines indicates the star's rotation rate and the presence of magnetic fields. The Doppler shifts of lines in binary systems allow mass determinations. This flood of information, combined with theoretical understanding of physics, allowed astronomers to construct comprehensive models of stellar structure and evolution, even though they could never visit a star directly or take one apart in a laboratory. The success of these models, their ability to explain and predict the diverse phenomena we observe in stars throughout the universe, stands as one of the great achievements of human intellect. It demonstrates that careful observation, combined with mathematical analysis and physical insight, can unlock secrets of objects so distant and so different from our everyday experience that they might have remained forever mysterious. Yet here we are, able to describe with confidence what goes on in the core of a star 15 million light-years away, to predict how it will evolve over the next million years, and to understand why it shines with the particular brightness and color we observe. This intellectual achievement carries with it a sense of wonder, a recognition that we are privileged to live in an age when such understanding has become possible. The predictability of stellar behavior is not a reduction of stars to mere mechanisms, stripped of mystery and wonder. Rather, it's an elevation of human understanding, a testament to the power of reason to illuminate even the most remote and seemingly inaccessible aspects of the cosmos. The more we understand about how stars work, the more remarkable they become, not less. To know that a star is held together by the delicate balance of gravity and pressure, that it generates energy through the transformation of matter at the most fundamental level, that it evolves over billions of years through stages we can predict and understand, this knowledge enriches our appreciation rather than diminishing it. The patterns we see in stars, the classifications we've developed, the relationships we've discovered between stellar properties, all point to an underlying simplicity in nature. Despite the bewildering variety of stars we observe, from tiny red dwarfs barely massive enough to sustain fusion to massive blue supergiants thousands of times more luminous than our Sun, from slowly rotating stars to rapidly spinning pulsars, from single isolated stars to complex multiple star systems, the same basic principles apply to all of them. Mass, composition, and age determine a star's properties through the operation of physical laws that are themselves surprisingly simple and elegant when expressed mathematically. This simplicity underlying complexity is a recurring theme in nature, from the few fundamental forces that give rise to all physical phenomena to the genetic code that directs the development of every living organism. Stars participate in this pattern, their rich variety emerging from straightforward physical principles operating under different initial conditions. Understanding this doesn't make the night sky less beautiful or less inspiring. If anything, it adds layers of meaning to what we see when we look up at the stars, transforming them from mere points of light into comprehensible objects with histories we can trace and futures we can predict. And so we come to the end of our journey through the stellar realm, a voyage that has taken us from the violent births of stars in collapsing clouds of gas and dust to their ultimate fates as white dwarfs, neutron stars, or black holes. We've explored the intricate nuclear reactions that power their cores, the delicate balances that maintain their stability over millions or billions of years, and the predictable patterns that govern their evolution from youth through old age to their eventual ends. Throughout this exploration, we've seen how stars, despite their almost unimaginable scale and the extreme conditions within them, obey physical laws we can understand and mathematical relationships we can describe. There's something deeply comforting in this understanding, something that speaks to our place in the cosmos. We are creatures who evolved on a small planet orbiting an ordinary star in an unremarkable region of a typical galaxy. Yet we've developed minds capable of comprehending objects so vast and so distant that light from them takes thousands or millions or even billions of years to reach us. We've learned to read the stories written in starlight, to decode the messages carried across intergalactic space in the form of electromagnetic radiation, and to construct mental models of stellar interiors that we can never directly observe but whose existence and properties we can infer with remarkable confidence. The stars have been constant companions throughout human history, appearing each night in their familiar patterns, marking the passage of seasons and guiding travelers across trackless oceans and deserts. Ancient peoples looked to them with wonder and wove them into their mythologies, seeing in the constellations the shapes of heroes and animals, the seats of gods and the destinations of souls. Even as our understanding has deepened, even as we've come to realize that stars are natural objects governed by physics rather than supernatural beings, they retain their power to inspire awe and contemplation. When you look up at the night sky now, armed with the knowledge we've explored together, you're seeing those same points of light with new eyes. That reddish star low on the horizon might be a cool red giant, having swollen to hundreds of times its former size as it nears the end of its life. That brilliant white star overhead could be a massive blue supergiant, burning through its fuel so rapidly that it will explode as a supernova within just a few million years. That faint reddish pinpoint might be a nearby red dwarf, so small and cool that it will continue shining for trillions of years, far outlasting nearly every other star in the galaxy. Each star you see is a sun in its own right, many of them probably accompanied by planets as our sun is, perhaps some of those planets bearing life, perhaps some of that life having developed consciousness and intelligence, looking up at their own night skies and wondering about the points of light they see there, perhaps pondering whether they're alone in the universe just as we do. The light from those distant stars left them years or decades or centuries or millennia ago, carrying information about conditions in those stellar photospheres at that time, information we're only now receiving and analyzing. The predictability of stellar behavior means that we can look at a star today and know not just what it is now but what it was in the past and what it will become in the future. We can trace the evolutionary path that brought it to its current state and predict the changes it will undergo over the millennia and eons to come. This ability to see through time, to understand the full life cycle of stars from birth to death, represents one of the deepest insights science has given us. It connects past, present, and future in a continuous chain of cause and effect governed by unchanging physical laws. There's a meditative quality to contemplating stellar timescales, those vast stretches of years that dwarf human history and human concerns. The oldest stars in our galaxy formed more than 13 billion years ago, when the universe itself was less than a billion years old. They've been shining steadily through all the eons since, witnessing the formation of countless generations of younger stars, the births and deaths of planets, the rise and fall of civilizations we'll never know about on worlds we'll never see. Our Sun is a middle-aged star about halfway through its main sequence lifetime, and it will continue shining with relatively little change for another 5 billion years, long enough that any civilization on Earth, if we and our descendants manage to survive, will have plenty of time to develop technology beyond anything we can currently imagine. Yet the Sun's entire lifetime, impressive as it is by human standards, is just one brief episode in the cosmic story. The universe has existed for 13.8 billion years, and it will continue existing for trillions of years more, long after the last massive stars have exploded and even after stars like the Sun have exhausted their fuel and faded to darkness. The smallest red dwarfs, those faint stars that barely qualify for stellar status, will outlive almost everything else, sustaining fusion reactions for hundreds of billions or even trillions of years before they too eventually exhaust their hydrogen and settle into slow cooling as white dwarfs. This vast temporal landscape can make human concerns seem small and fleeting, and perhaps that perspective is valuable. The stresses and worries that occupy our daily thoughts, the fears about the future that can keep us awake at night, all exist against the backdrop of a cosmos that unfolds according to its own timescales, utterly indifferent to our anxieties. Stars don't worry about their futures. They simply exist, following the paths laid out by their masses and compositions, burning their fuel at the rates determined by physics, evolving through stages that were inevitable from the moment they formed. There's a peace to be found in this realization, a sense that the universe has its own order and rhythm that continues regardless of our individual circumstances. When everything feels chaotic and uncertain, when human affairs seem overwhelming in their complexity and unpredictability, we can look to the stars and remember that on the largest scales, nature follows comprehensible patterns. The same star you see tonight will be there tomorrow night and the night after that, shining with the same steady light, maintained in equilibrium by forces that have operated without interruption for millions or billions of years. This doesn't mean that our individual lives lack meaning or importance. Rather, it provides context, a reminder that we're part of something much larger than ourselves, participants in a cosmic story that stretches from the Big Bang to whatever ultimate fate awaits the universe trillions of years hence. The atoms in our bodies were forged in stellar furnaces and scattered into space by dying stars, making us quite literally children of the cosmos, made of star stuff, as Carl Sagan so eloquently put it. The iron in our blood, the calcium in our bones, the oxygen we breathe with every breath, all of these elements were created in stars and returned to space when those stars ended their lives, later to be incorporated into new stellar systems including our own. This connection to the stars is not merely poetic. It's a matter of established scientific fact. We are tied to the cosmos through chains of cause and effect that stretch back billions of years. The sun that warms our world and powers almost all life on Earth is a star, a nuclear fusion reactor suspended in space, held together by its own gravity and sustained by the conversion of hydrogen to helium in its core. The light that reaches us left the sun's surface about 8 minutes ago, having worked its way up from the core over hundreds of thousands of years, carrying energy that will drive photosynthesis in plants, warm the oceans, create weather patterns, and ultimately support the entire biosphere. In contemplating these truths, in reflecting on the nature of stars and the physical laws that govern them, we're engaging in an activity that's uniquely human, the pursuit of understanding for its own sake. No other species on Earth, as far as we know, wonders about the nature of stars or seeks to understand the mathematical relationships that determine stellar properties. This capacity for abstract thought, for scientific reasoning, for mathematical analysis. These are gifts that allow us to transcend our biological origins and grasp truths about the universe that have nothing directly to do with survival or reproduction. The predictability of stellar behavior, the fact that we can understand and predict how stars work, testifies to the power of this human capacity. It shows that the universe is, at least in part, comprehensible to minds like ours, that the patterns in nature are patterns we can recognize and describe. This comprehensibility is itself a profound and somewhat mysterious fact. Why should the universe be mathematical? Why should the laws of physics be expressible in the language of mathematics? These are deep questions that philosophers and physicists continue to ponder, but the fact remains that mathematics works, that it allows us to describe natural phenomena with extraordinary precision and to make predictions that observation consistently confirms. As we close this exploration of stars and their behavior, let's take a moment to appreciate not just the stars themselves, but the entire edifice of knowledge that humanity has constructed to understand them. Every fact we've discussed, every relationship we've explored, represents the culmination of centuries of patient observation, careful experimentation, creative theoretical work, and mathematical analysis. Thousands of astronomers, physicists, and mathematicians have contributed to this collective understanding, each building on the work of those who came before, gradually refining our models and extending our knowledge. This knowledge is one of humanity's greatest achievements, a testament to what we can accomplish when we apply reason and observation to understanding the natural world. It's also a living body of knowledge that continues to grow and develop as new observations reveal phenomena we didn't anticipate and as theoretical advances allow us to make more precise predictions. The process of science is never truly complete. There are always new questions to ask, new puzzles to solve, new frontiers to explore. For those of us fascinated by the cosmos, this ongoing process of discovery is endlessly exciting. Every new generation of telescopes reveals objects and phenomena we hadn't seen before. Every advance in computer technology allows more sophisticated simulations of stellar processes. Every improvement in our understanding of fundamental physics refines our models of stellar structure and evolution. We're fortunate to live in an era when our tools for observing the universe have become extraordinarily powerful, when space telescopes can observe in wavelengths blocked by Earth's atmosphere, when interferometry can achieve angular resolutions finer than any single telescope could manage, when massive computational resources allow simulations of unprecedented complexity and realism. Yet, for all these advances, the fundamental picture of stellar behavior we've developed remains robust. The basic framework of understanding we've built, stars as self-gravitating spheres of plasma sustained by nuclear fusion, evolving through predictable stages determined by their masses and compositions, ultimately leaving behind compact remnants or dispersing their material into space. This framework has stood the test of decades of increasingly precise observations. The details have been refined, subtle effects have been incorporated, and our understanding has deepened, but the core insights remain valid. This robustness gives us confidence that we've truly grasped something fundamental about how stars work, that our models capture the essential physics even if details remain to be worked out. It also means that the knowledge we've shared in this journey is not likely to be overturned by future discoveries. The stars will continue to obey the same laws of physics, to follow the same evolutionary paths, to exhibit the same patterns and relationships we've described. Future astronomers may learn things we don't yet know, may discover new types of stars or new stellar phenomena, but they'll understand them through the same physical principles we've explored together. So as you settle into rest, as you allow your mind to drift towards sleep, you can do so with the comforting knowledge that out there, across the vast dark between the stars, countless suns are shining according to predictable patterns, following paths determined by physics, maintaining their steady light through the operation of forces we understand. The universe is not chaos. It's not random or arbitrary. It operates according to rules, and those rules are ones we've learned to decipher and describe. Perhaps tonight, as you close your eyes, you might imagine yourself floating peacefully in space, looking out at the countless stars surrounding you in all directions. Each one is a sun, a nuclear furnace sustaining itself through fusion, balanced between gravity and pressure, shining with a luminosity determined by its mass and age. Some are young and hot, blazing with fierce blue-white light. Others are old and cool, glowing with a soft reddish radiance. Still others are in the throes of dramatic evolution, swelling into giants or shedding their outer layers or building up to the explosive finale of a supernova. But all of them, every single one, follows the same physical laws. All are governed by gravity, sustained by fusion, structured by the interplay of pressure and temperature. All can be understood, at least in principle, through the application of physics and mathematics. There's a profound unity to this, a simplicity underlying the diversity, a set of common principles that apply throughout the cosmos. Let this knowledge bring you peace. Let it remind you that even in a universe so vast that it challenges comprehension, there is order and pattern. The stars shine on, reliable and predictable, constant points of light in the darkness. They shone before we existed and will continue shining long after we're gone, indifferent to human concerns but also in their constancy and predictability, offering a sort of cosmic reassurance. The universe is old, far older than human civilization, older than life on Earth, older than Earth itself. Yet it continues to unfold according to physical laws that, as far as we can tell, have remained unchanged throughout cosmic history. The same laws that govern stars today govern them in the early universe billions of years ago. The same principles that determine stellar structure in our galaxy apply in galaxies billions of light years away. This consistency, this reliability of natural law across space and time, is one of the most remarkable and reassuring discoveries science has made. As you drift off to sleep, you might find comfort in the thought that you're a part of this cosmos, made of the same elements forged in stellar cores, subject to the same physical laws, connected through chains of causation to events that occurred billions of years ago in the hearts of stars that no longer exist. You're a temporary configuration of matter and energy, yes, but what remarkable matter and energy it is, organized in such a way as to be capable of contemplating its own origins and the nature of stars themselves. Sleep well, knowing that the universe continues its stately dance, that stars are being born in clouds of gas and dust even as you rest, that others are dying in spectacular explosions that seed space with the elements of future worlds, that the great cosmic cycle continues, driven by gravity and nuclear physics and the other fundamental forces. The night sky above, whether you can see it or not, is filled with stars, each one following its predetermined path through space and time, each one a nuclear furnace burning bright against the cosmic dark. And tomorrow night, and the night after, and for countless nights to come, those stars will still be there, shining with their predictable light, waiting to be observed and wondered at by anyone who takes the time to look up and contemplate the marvelous universe we're privileged to inhabit. The patterns we've explored, the relationships we've described, the physical laws we've discussed, all will continue operating as they have for billions of years, maintaining the cosmic order, keeping the stars shining, and demonstrating through their behavior that the universe, for all its vastness and complexity, is ultimately comprehensible to minds willing to observe carefully and think deeply. Before we part ways, I want to express my gratitude that you've joined me on this journey through the stellar realm. Exploring the cosmos through the lens of science is one of humanity's great adventures, and every person who takes the time to learn about stars and their behavior becomes part of that adventure, a participant in the ongoing human quest to understand the universe we inhabit. If you've enjoyed this relaxing exploration of stellar physics and astronomy, if you've found value in understanding how stars work and comfort in the predictability of stellar behavior, I'd be grateful if you'd take a moment to like this video and subscribe to the Deep Science Sleep channel. Your support helps make it possible to continue creating these long-form, in-depth explorations of scientific topics, these journeys through the realms of knowledge that can both inform the mind and soothe the spirit. There's so much more to discover, so many more topics to explore, so many more fascinating aspects of the natural world to contemplate. From the quantum realm where particles behave in ways that challenge intuition to the cosmic realm where galaxies collide and black holes merge. From the biological realm where evolution crafts endless variations on the theme of life to the geological realm where continents drift and mountains rise, the universe offers endless opportunities for wonder and learning. Each video on this channel represents hours of research, writing, and careful consideration, all aimed at bringing you accurate information presented in a relaxing, conversational style that makes complex topics accessible without sacrificing scientific rigor. By subscribing, you're not just helping the channel grow. You're supporting the creation of educational content that respects both your intelligence and your desire for peaceful, contemplative learning. The universe is vast, full of wonders, governed by physical laws we can understand. The stars shine on, following their predictable paths, and we, brief sparks of consciousness in the cosmic dark, are privileged to observe them, study them, and come to understand them. May that understanding bring you both knowledge and peace, both intellectual satisfaction and emotional comfort. Thank you for spending this time with me, exploring the predictable beauty of stellar behavior. May your dreams tonight be filled with stars, each one shining bright according to the eternal laws of physics, each one a reminder that in a sometimes chaotic universe, there is underlying order and pattern. Sleep well, and I'll see you in the next video for another peaceful journey through the fascinating world of science. Until then, look up at the stars whenever you can, and remember, they're not just points of light in the darkness. They're nuclear furnaces, vast spheres of plasma, cosmic laboratories where elements are forged and physical laws are demonstrated on the grandest scales. They're reminders of our deep connection to the cosmos, proof of the power of human understanding, and eternal companions in the endless night. Good night, and clear skies to you always.